So, good morning, everyone. Welcome to ELIXIR CZ Friday Coffee. Today, we'll enjoy our coffees here with Vojtech Spiwok from University of Chemical Technology in Prague, who will be speaking how to make your molecular dynamics and metadynamics quicker with approximation of collective variables by neural networks and his package Anncolvar. Vojto, the floor is yours.
Thank you very much. Good morning. So it will be my great pleasure to introduce you our package. And first I will start with molecular dynamics simulation. So here you should see the movie of 3 different simulations, each containing a small protein called Hevane domain and either mono, di, or trisaccharide derived from chitine. And as you can see, in all simulations, we observed the binding of the ligand into the binding site. And in one simulation, we further observed like one unbinding and another binding in 2 microsecond simulations. So this somehow like implies that it would be possible to use such an approach to test some potential drugs, like to make a system containing protein, ligand, water molecules, and to simulate it long enough to see binding. But there are some limitations, and one limitation is that from these simulations we can only say that the ligand binds to the protein, and we can predict how it binds. But we know very little about the strength of binding, because for this it would be necessary to observe multiple binding and unbinding events. And this is quite non-realistic in classical molecular dynamics simulations, because some drug molecules can stay on its target for a very long time, even weeks, and we can simulate nanoseconds or microseconds, but not much longer. So it's necessary to somehow accelerate simulations, and the problem is that the bound state and also the unbound state represent some free energy minima, some local or global free energy minima, which are separated by some barriers. And the reason why simulations are so slow is that there is very little probability to cross such a high barrier in some short time. And for this, we can use the method which is our very favorite, called metadynamics. Here you see the illustration of metadynamics algorithm on a model energy surface, which is a profile of Giro d'Italia stage from, I think, 1914. And as you can see, that if we start from some local energy minimum, that metadynamics somehow force the system to get to the global energy minimum by flooding the local energy minimum, and by further flooding of the global energy minimum, it can make system to go back to the previous minimum, and at the end the system can freely move between all relevant minima of the system. So this is a very powerful method, and for this we need some. So here it's how it looks like when we apply metadynamics on the system, on the movie, which I've shown on one of previous slides. So we observe just one binding, and in one case one binding, unbinding, and another binding. But using metadynamics, we can see hundreds or tens of binding and unbinding events, which is like a bound state is low value, unbound state is high value, in the same length of simulation. So it's also like 2 microsecond simulation. And for this, we need something which is called collective variable. So metadynamics applies some artificial forces on some predefined descriptor, predefined variable, which we call collective variable. For binding and unbinding, the natural choice of such a collective variable is the distance between the binding site and the ligand. So we can, if the ligand stays bound for a long time, we can force it to unbind, and other way around. And but for some more complex system, it's necessary to look for some more sophisticated collective variables. So collective variable must be some good descriptor of the studied process, and it should make it possible to distinguish all key states. So for example, this distance is low for bound state and high for unbound state. It must be a function of Cartesian coordinates with finite derivative. So you can easily calculate the distance in Cartesian coordinates by Pythagoras theorem, and you can easily make its derivative. But this could be a problem, for example, for some promising collective variables such as nonlinear dimensionality reduction methods. So there are popular nonlinear dimensionality reduction methods like t-SNE or isomap. And you can take a set of data, you can analyze them with t-SNE or with isomap, you can get a nice map with thousands of points. But if you want to analyze another sample and make another point among these points, this is quite a problem. There is no straightforward way how to do it for these techniques. So this is one of motivations for our package. For biasing or for metadynamics, it's necessary that the collective variable should account for all slow processes. So for example, for some complex conformational changes or for protein folding, it's difficult to achieve this by some simple geometric variables like distances or torsions or things like that. And it's necessary to calculate this collective variable quickly, because it's being calculated during the simulation in each step. So this could be a problem for some crazy collective variables, such as solvent accessible surface area, which is normally calculated that the program takes the structure, for example, of protein, takes some probe which represents the water molecule, and somehow rolls this probe on the surface of protein, and from this it calculates the solvent accessible surface. But this is, if you can imagine that this would be very, very slow if it's calculated in every step of MD simulation. So our idea was to use neural networks to do this task, and my favorite neural network to explain neural networks is like there is an app on Google Store which you can install to your phone, and you can use it to recognize mushrooms. So the app takes a picture of a mushroom, it somehow resamples the picture and converts it into different color channels, and each intensity of each pixel in each channel is used as an input, which is then passed through the neurons in several layers of neural network, and at the end you got some vector which gives you the probability of being different mushroom species. So we get inspired by this, and instead of pixels or intensities of pixels, we took Cartesian coordinates of atoms, and we used the neural network to convert them into the value of collective variable. And this is the story behind Anncolvar. So this can fix the problem that for example, nonlinear dimensionality reduction methods, because you can take your data, analyze them, for example, by t-SNE or isomap, you get thousands of points, and you can train the neural network to predict, to somehow convert high dimensional data to low dimensional data, and then you can use this neural network instead of the method itself. And it works very well because it's everything which is transformed by a neural network is like a function with a finite derivative. And also, if I go back to this mushroom app. So some person who developed this mushroom app had to collect thousands of images of mushrooms to train the neural network and to get all the parameters of each neuron. And this task probably has been very computationally expensive, and it was necessary to use some very powerful computer to do this. But once the model is trained, you can record it into your mobile phone, which has very little computation power, and you can go to wood, and you don't have to take some supercomputer with you, or you don't have to be connected online to a supercomputer. And this application to one sample is very fast. So this is also good for us, that like this calculation via this neural network is reasonably fast. So here are some systems where we tested it. So first we started with some very simple system, which is like a cyclooctane derivative. Cyclooctane, this molecule, can exist in different conformers, and using isomap we can map these conformers into three-dimensional space. So it's like some ball with some kind of hourglass inside. If you do it by isomap, it's like a perfect ball. If you approximate it by our method, it's a little bit like ball which was fallen down from somewhere, but it's still good for our purpose. And different conformers correspond to different places on these in these points. And using this, we were not only able to accelerate different conformational transition between these different conformers, but also calculate free energy values for these conformers, so to predict some equilibria and also some kinetics of some conformational changes in this molecule. So then we switched to some more complicated molecule, and we started with a mini protein called tryptophan cage. It is a artificial fast folding 20 amino acid mini protein. We took some long trajectory of this mini protein where there were some folded and unfolded states, and for each snapshot we calculated solvent accessible surface area by conventional method. And we used this information to train the neural network and to approximate this solvent surface area by a neural network. And here you can see some very good correlation between the true solvent accessible surface area and the solvent accessible surface area approximated by our method. And it's natural that for some folded protein, we would expect to have some smaller solvent accessible surface area than unfolded protein. And so we accelerated folding and unfolding, and we were happy to observe some realistic free energy surfaces. So the folded state is in this, I don't know if you see my cursor. So it's like this low value of on horizontal axis and a little bit bigger value on vertical axis. So this is like the global minimum at low temperatures, but at higher temperatures this folded state is naturally destabilized, and the system prefers unfolded state, which is in agreement with the behavior of proteins. And finally, what we did, we applied it on a little bit bigger mini protein called Villine. And what we approximated by our neural network was a Rosetta score. That is a program which is very successful in prediction of three-dimensional structures of protein called Rosetta. And in principle, it would be possible to somehow implement this into the code which we use for molecular dynamic simulation and acceleration by metadynamics, but it would be quite complicated. So again, we took we generated large samples of structures of the protein. We approximated their score by Rosetta package, and then we used an Anncolvar to approximate it via neural network on the fly during the metadynamic simulation. And again, we were able to accelerate significantly folding of this mini protein and accurately predict its free energy surface, like that the folded state, which is again like some higher value of on the horizontal axis, is dominant at low temperatures and becomes less favored at higher temperatures. If you are interested in using this package, it's available on GitHub, and it's a Python package, so you can install it using pip or conda. And once you install it, it installs also some necessary components. So it uses Keras, which is a very nice machine learning package, and this Keras runs on top of one of 3 different backends, so you can choose between TensorFlow, Tieno, or Microsoft Cognitive Toolkit. And you have to supply the trajectory, some series of structures of your molecular system. You have to supply some reference structure, and you supply the file which contains the value of your collective variable. So, for example, some isomap embeddings or solvent accessible surface area or whatever you want. You have to somehow design the neural network by specifying number of layers, number of neurons in each layer, and different activation functions. And you can also influence some other parameters which are not listed here. You have to choose a number of epochs, and if you use batches in the learning process, you have to specify batch size. And the output is like approximated collective variable, and you also get the file which can be directly used in popular metadynamics or enhanced sampling package called Plumed. And Plumed can be used with many different molecular modeling or biomolecular simulation packages, so you can directly use it with your favorite biomolecular simulation package. So in this Plumed, there is the whole description of the neural network, everything that Plumed needs to calculate from coordinates your collective variable. And you can use it either for analysis, or you can use it in metadynamics or other methods which are available in Plumed for sampling enhancement. There are 2 versions of files, because at the beginning we made this neural network in a form of a function, mathematical function. So, and there are hundreds of different parameters, so it's quite big file. And later this was replaced. There is a new module for a neural network in Plumed, introduced by a lab of Andrew Ferguson, and so we provide these the file with also this alternative input. So that's all. I would like to thank all my collaborators from our university, and also people from Aleš Křenek group who are intensively working on also acceleration of calculation of collective variables by neural networks. And I would like to thank you for your attention, and I will be happy to answer your questions.
Thank you. That was a really nice lecture, and there are 3 questions already, and I have one myself. So I'll start with Robert. His first question is how to create the initial training set. For example, for protein interactions with drug. Shall one pull the drug towards the protein and out and use these system configurations for training?
So yeah, I think everything is allowed, because it's not necessary to somehow make structures to represent some thermodynamics of the process, because you should calculate the thermodynamics by metadynamics. So if you use anything which makes some reasonable structures, then it should work properly. So for some conformations, we used either some long trajectories, which is a little bit like problematic, because it's kind of chicken and egg problem that you need long trajectories to make a model using which you want to calculate long trajectories or simulate long processes. So this is not perfect, but for example, with this Rosetta package, it was very useful, because it can very efficiently create some realistic conformations of the of some protein, and we can use them as a training set. For protein ligand binding, I'm not aware of any kind of clever trick how to generate some huge number of realistic poses of ligand in versus target. Maybe some
Docking.
You can use docking with some like relaxed settings, like to make that you are not interested really in the minimum, but you want to map somehow. So this would be possible.
And my question then is it possible then to use the protein ensemble, such as from protein knowledge base or from protein ensemble database or something like that? Or even from the predictions, like using the models from AlphaFold and Swiss model and Modeler, something like that?
In principle, yes. I'm not sure if it's good for a neural network to have a lot of data, a lot of points, so like thousands or tens of thousands. So I'm not sure how it would be possible to generate like tens of thousands potential structures and like a diverse set of potential structures. So this is maybe too much for AlphaFold, but I think reasonable for some other methods.
Mm-hmm. Okay, so next question from Robert. How shall one estimate what should be the neural network properties? Size, number of layers, and something else?
So we use kind of trial and error to determine this, but of course it will be good to have something more sophisticated. So there is no clear answer to this. I would say, like in terms of learning rate, loss, and optimizer, I think we found the something which works, and we found that other optimizers or other loss functions do not work. So those are like default in our package. Some other optimizers which are available, for example, in Keras, there are some other loss functions. We found that they do not work very well. And they are still available, but not default. So, somebody can switch them on. But in terms of like architecture, it's difficult to say.
Mm-hmm. Thank you. And then Robert will ask his questions himself.
Just a follow up on that. I understand that there is a lot of unknown for that, but is there a sort of a systematic way what to try or how to approach it, not just by trial and error? And that I mainly mean for the neural network design.
So I'm not aware of any like some systematic approach in doing this. So we usually start from some small network and go to larger one. And I think that adding layers in the network, it can be used if you feel that there is some kind of like a non-linearity in the relation between, or a high non-linearity between in a relation between coordinates and your collective variable. So then it's good to make rather more smaller layers rather than few bigger layers. So that's.
If I may, the last question. So what if one uses your package and then still finds hysteresis in the metadynamics? So it's clear that the collective variable is still not the right one, but how shall one know if to change the neural network or if to change the sampling of the system? Like how to find where is the problem?
So it may happen that, for example, a neural network is trained on some insufficient data. So it's easy to use our package or the output of our package to recalculate the new data sampled by, for example, metadynamics, and to compare it with some collective variable calculated by a conventional way. And then you will see whether it's because of the collective variable you decided to use doesn't work, or whether it's our package which doesn't properly approximate the correct collective variable. So typically, like if you train your this collective variable on some unfolded protein, and then you in the simulation you get to the folded state, but there is something wrong going on, then you can check whether it approximates correctly the collective variable on the folded state.
Okay, perfect. Thank you.
Okay. Is there any other question? If not, then thank you, Vojta, again. And we'll meet next week over the next Friday seminar, which will be the SBC, the R package for simulation-based calibration and validation on statistical models and algorithms, which will be taught by Martin Modrák. And I want to point you all that we have a YouTube playlist for these Friday coffees that you can find on YouTube of the ELIXIR Check. So thank you all for listening. Vojta, once again, thank you for your lecture and have a nice Friday. Bye.